Hi everybody, this is lecture 9 and today we will do a review for midterm 1. So the sections that we'll cover that will appear in midterm 1, the material for midterm 1 is what we've covered so far in our course, so everything starting from section 15.1 on double integrals and ending in section 15.9 where we talked about change of coordinates. In the middle, there's triple integral, cylindrical coordinates, everything that we've discussed. So some of the material will not be tested directly, but may appear indirectly. For example, the review of vectors, even though there won't be questions asking you specifically about cross products, there will be, in this exam, there may be questions that relate to that. So, but they won't be tested. But the review of vectors from chapter 14 won't be tested directly. All right. So now let's, before we begin, so today I just want to do a bunch of examples, a bunch of calculations. But before we begin, one final comment is a tip for you. So if you want to practice for the exam, do check out the Professor Andrew Lovelace's exam archive. This is linked from our course website, and you shouldn't stress about doing all of the old exams, but I would recommend doing 1 or 2 for practice so you're not caught, you're not surprised by the midterm you see next Monday. Also, I strongly advise you, you don't want the exam contents, the math to be a surprise. But you also don't want the technology to be a surprise on Monday. So for this reason, I strongly advise you to head to Gradescope, sign up for Gradescope, log into our course, play with the sample exam, so the technology isn't something you have to figure out on the day of the exam. So do it like today. And do check out Gradescope using your phone, because on my phone it's easier than just using the computer. Because on the phone, when you tap to upload your solution, you don't have to choose a file. There's an option to just shoot up to open the camera app on your phone, and then when you tap select file, you can just take a picture of your handwritten work and submit it from there. All right. So enough about the organization of the course. Let's discuss some math. So here's the first example. Let's start slow. So the first example is about changing the order of integration. So here is the double integral. So let's see. Look at my notes. So we're integrating. So here we don't have to evaluate anything. So the outer bounds are 0 and 4. The inner bounds are root y and 2. And we have some function of x and y. And our job is to change the order of integration from dx dy to dy dx. So we have to fill in the bounds in the order dy dx. Okay. So to do this, you should not go straight from the old bounds to the new bounds. We should absolutely draw a picture of this region of integration. Okay, so here this region is, so there's the dy integral, so that's outside. So the bounds are 0 and 4. This means the minimum y coordinate of a point of any point in the region of integration is 0, and the maximum y coordinate of any point in the region of integration is 4. And then x is between root y and 2. So that's root y is the positive, by convention, the positive square root. So so x is between some positive number and 2. So you see that our region will be in the first quadrant, because x and y in this region of integration are always non-negative. So let's start drawing the region before filling in the bounds in the other order. Okay, so we know that the minimum value of y is 0. And the maximum value of y is 4 on this region. Okay, so up here, y is equal to 4. And then for an intermediate value of x, so for an intermediate value of y, x goes from root y to 2. So x always stops at 2. So this is always the last value of x. Maybe I should draw it to a better scale like this. So here's 2. So x always stops at 2, and it starts at the curve x equals root y. So what does this curve look like? So here maybe some scratch paper where x equals root y. So that's the same as saying that, well, not necessarily the same as saying, but this implies that x squared is equal to y. I can't really go back because of the sign. So this equation here doesn't actually. Well, I can't go back because of the sign of x. So this equation over here could permit x to be positive, x to be negative, but this one necessitates x to be non-negative. Okay, so this is y equals x squared, so that's just a parabola. So let me draw that parabola over here. Right, so this equation over here is y is x equals root y. Or in other words, I mean, if we know in the first quadrant, we can really go back and forth. X squared, y equals x squared. Okay, let me delete the scratch work over here. Now, what the inner integral is telling us is that for an intermediate value of y, so between 0 and 4, so if I fix an intermediate value of y, x is going from root y to 2. So x starts at root y. So here's y, here's x being equal to root y, and x stops at 2. So this is the integral, the region of integration. So it's being, in the order of integration given to us, it's being cut like this. Now, so this other integral over here, so in the other order, we're talking about an integral that's slicing a region with vertical line segments rather than horizontal ones. Right, so let's fill in the balance for here. X goes, so the minimum value of x in this whole shape, this whole region of integration is 0, and the maximum is 2. So x goes from 0 to 2. And if I give you an intermediate value of x, y goes from down here to up here vertically. So it starts, y starts at 0. Let me put the name of the variable so it's easier, so we don't get confused. So x starts at 0, stops at 2. Y starts at 0 and stops at x squared. So there you go. This solves the problem in this case. So what I would like to emphasize is that a problem about filling in bounds, changing order of integration. So most of the time, when you're giving an integral, you probably want to draw the region of integration. So very often, maybe if not most of the time, very often, if you're giving a problem about an integral, and you have to change the order of integration or set it up in a different coordinate system, you have to draw the region of integration. Okay, so next problem is about change of coordinates. So let's get to it. So example. So in this problem, we have to compute the double integral of, so this double integral over some region D. I will draw the region in a second of e to the 8x squared plus y squared dA. So this is the integral we want to compute, and D, this plane region D is this 2D shape is the interior of an ellipse. So D is the interior of an ellipse, and the ellipse is the equation, basically the equation of a circle, but one of the variables is rescaled. So to understand what ellipse we're talking about, let me draw it over here. So I'll draw it on this side, kind of squeeze it here. I'm leaving some room on the left because the problem tells us to do an appropriate change of variables to evaluate this double integral. So the change. So here I'm drawing the xy plane. We'll introduce new variables u and v, and draw. And once we understand what first we'll understand what this ellipse looks like here in the xy plane, and then I'm going to figure out what the right coordinates are and draw the corresponding shape, simpler shape, in the UV plane. All right, let's do it. So I'm going to do this just by observing. So this is really a circle. So it's basically a circle, but I'm rescaling one of the variables, and then you stretch it, and if you stretch it in one direction or another, a circle becomes an ellipse. But exactly what ellipse are we talking about? Well, so let's sample a few points in here. So one point, for example, is if y is 0, then I get the equation x squared equals 1, so x is plus or minus 1. So here's 1, here is minus 1. 1 and minus 1. Okay? Now, if, on the other hand, if x is 0, instead of y, x is 0, then y over 2 root 2 squared is 1. So y over 2 root 2 is plus or minus 1. So y is equal to plus or minus 2 root 2. So here is plus 2 times root 2, and down here is minus 2 times root 2. And our region our ellipse is this. Our region of integration looks like this. So it's stretched vertically. So it's taller than it is. This ellipse is taller than it is wide. Let me try to improve this picture. Nice. I like nice pictures. Okay. So this is, it's not nice. Ellipses are clunky to work with in Cartesian coordinates. So what we're going to do, but circles are nice. So what I propose we do in this case is to try to figure out a change of coordinates where this ellipse, so introduce new variables u and v that make this ellipse become a circle. So here's going to be, so we're going to use new coordinates u and v. Oops. With the problem, and then there's some transformation. If I have to tell you a rule, if I know what u and v are, what x and y are, and vice versa. So I want the ellipse to look like a circle in the UV plane, the unit circle, standard unit circle. So this is I'm going to call this circle R, really a disk, and the original region, which is an ellipse, I will call it D, not for disk, but for ellipse. I won't call it. I have been calling it D, so there's a label. There's the appropriate label. Okay, so I want the transformation that makes this ellipse become a disk. And I'm looking at this equation, so this disk will have this. So the equation of the corresponding shape in the UV plane is this equation translated to the new coordinates. So if I want this to be u squared plus v squared equals 1, the equation of the standard disk, I know what I have to do, right? I want v, so the new coordinate v should just be x, and the new coordinate u, the new coordinate u should just be x, and the new coordinate v should just be y over 2 root 2. Can you see? Because if I do this, then this circle over here has equation, the two shapes have equation u squared plus v squared equals 1, the two boundary curves. So this succeeds in making my region of integration into a circle. But now we must ask ourselves, so making this change of variables will simplify the region of integration, but will it complicate the integrand? So let's see. So 8x squared. So what's 8x squared? So what's x? Let's figure this out. So x colors are kind of confusing. So let me solve for x and let me write x and y in terms of u and v. So the old coordinates in terms of the new. So x is just equal to u, and y is equal to 2 root 2 times v. Okay, so 8x squared plus y squared is equal to 8u squared plus v squared, sorry, y squared, but y squared is 2 root 2 squared times v, and 2 root 2 squared is 4 times 2, that's 8 times v. So this is what we get. Okay, 8 times u squared plus v squared is a manageable integrand. So let's proceed with this, with these coordinates u and v. So maybe so I think that this is something I can try to integrate. So that's why I'm going to go on with this with these coordinates I proposed. If this had turned out to be a really ugly thing, I would maybe try a different set of coordinates. You know, allow the region R to maybe be a little bit more irregular, but in order to make the integrand nicer. But this one is fine, so we can continue with this choice of coordinates. Okay. So so here's what we're gonna need. So dA, so that's dx dy, is a certain multiple of du dv, and the multiple is the Jacobian determinant. So let's figure out the Jacobian determinant. So that's d of x comma y divided by d uv, which is just, you know, funny notation for the determinant. Let me give myself some room here. It's funny notation for the determinant of dx du, dy du, dx dv, dy dv. Okay, so let me just note that sometimes you'll see this formula, this matrix flipped, so the transpose of this matrix in the definition of the Jacobian determinant, but that doesn't make a difference. So that having the matrix or a transpose doesn't make a difference because the determinant of any matrix is equal to the determinant of the transpose of that matrix. So some books may have different conventions. You know, different sources will have different conventions for this definition, but they don't matter. I mean, the matrix you put here, it doesn't matter if you replace it by its transpose. All right, let's now compute this in the case at hand. So we're talking about the determinant of, so dx, to compute dx du, to compute these partials, I need to write the new variables in terms, purely in terms of, sorry, I need to write the old variables purely in terms of the new ones. So I already did this up here. So to compute the partials, I need formulas for the old variables purely in terms of the new ones. So I can't, for example, have a formula for y that involves u and x, and then, you know, that's not something we want to do. Okay, so let's do that. So dx du. So x is u, so dx du is 1. dy du, so y is 2 root 2 times v, so the u partial here is 0. Okay. Next, dx dv is du dv, that's 0. All right. And finally, dy dv is 2 root 2, is just 2 times root 2. So this determinant is just 2 times root 2. That's another important ingredient when we compute when you change variables. Okay, so the integral we had, let me give that integral a name. So I'll call this integral I for integral. So the integral we're supposed to compute, that's the double integral. So it can be evaluated in terms of the variables u and v as a double integral over r, this unit circle in the uv plane. And then we're integrating e to the 8 times u squared plus v squared. And then multiplied by the absolute value of the Jacobian determinant times du dv. Now this absolute value of the Jacobian determinant is 2 root 2, so its absolute value is also 2 times root 2. Okay, so we have a slightly better looking integral, but that's still, we still don't want to compute this this integral here directly in terms of u and v, right? Because I mean, it's this integral is really begging us to use polar coordinates, right? So the region of integration is disk, and in the uv plane, and the function we're integrating is a function of, really depends on u squared plus v squared, which is the distance from the origin of the uv plane. So what I'm going to do is to use polar coordinates in the uv plane. So introduce polar coordinates in the uv plane. So u is r cosine theta, and v is r sine theta. Now if I do that, I get this integral over the unit circle, which becomes an integral in theta going from 0 to 2 pi, an integral in r going from 0 to 1, because this is the unit circle, and then we're integrating e to the 8r squared times, well, there was that 2 root 2, which I didn't pull out of the integral, so just repeat that, times du dv, that's r times dr d theta. So, so a few things can come out this integral. So for example, the 2 root 2 comes out. Now the answer to the dr integral won't depend on theta, so that's a constant that I can pull out of the d theta integral, and then the d theta integral just results in a factor of 2 pi. And the integral with respect to r, so what's the integral of this exponential times r? So it's I mean, you can see that r is basically the derivative of 8r squared. The derivative of 8r squared is 16r. So I'm going to fix that by dividing by 16. So the integral of e to 8r squared times r is 16 times what we were integrating before. So I divide by 16 and then I'm able to evaluate. So this is what we get. So we have root 2, so 4 times, so the result is root 2 over 4 times pi times e to the 8th power, that's 8 times 1 squared, minus e to the 0, which is 8 times 0 squared. E to the 0 is just 1. And that's the answer of our integral. Okay, so there you go. I think this is a good example showing how changing variables allows us to, extends our reach. So to begin with, we're able to work with straight lines, with the parabolas and circles, right? Once we introduce, in Cartesian coordinates, we were happy to work with triangles and parabolas and things like that. Once we introduced polar coordinates, we were happy to work, for example, with circle. We're very happy to work with a circle around the origin when doing integrals. Now with change of coordinates, we can move these shapes around. So for example, if I do a change where y stays the same but the new variables are x minus 1 and y, I'm really shifting the whole plane horizontally. So you can do translations with changes of variables. You can rescale things in different directions by doing, if you know a little bit about linear algebra, and if the transformation is given by a 2x2 matrix, you can also do rotations, a bunch of interesting things. So it greatly expands, so this ability to change of coordinates greatly expands our reach, allows us to handle many, start with a basic set of shapes we know how to work with, and allows us to work with more complicated shapes. So, which are related to those. One final comment before we leave this example is you guys may have noticed that I really did two changes of variables. The first one was from x and y to u and v, and then I changed from u and v to r and theta. So I could have done this in a single step. So in a single step, the change would have been, I could have introduced new variables like this. I could have said that, so here, u is r cosine theta, but u, so x is u. So in a single step, I could have said that x is u, which is r cosine theta, and y is 2 root 2 times v, so that's 2 root 2 times r sine theta. But then, so I could have done this integral by using a single change of coordinates, but I would be using these funny r and theta, which are, so I'd be using r and theta coordinates on the uv plane, not on x and y. So here r and theta, so in these formulas, r and theta are not the usual ones you know, they don't give you the usual notion, the usual distance and angle in the xy plane. They're just names for variables, and what those variables really mean is distance from the origin and angle, but in a different plane. So if I had done this change of variables in the beginning of this calculation, I wouldn't have needed to do a second change of variables. So might have saved time, but I think it's important to emphasize that we don't have to really rush through things most of the time. I mean, it's usually best to do one small thing one small operation at a time. Okay, so we're ready for the next problem. So here it is. So this comes from the exam archive. So we're given a region. And we know, so E is a solid region, and we know it's inside the unit sphere. So, inside the first quad octant, where x, y, and z are all non-negative. It's inside the sphere. Oh yeah, so I was right. So inside the unit sphere. So these are all points whose distance from the origin squared is at most 1, and it's below the plane where z is equal to y. So I should note that by saying below here, I'm saying that z points up. And when I say below, I'm using the convention that z points up. This is a convention that we use most of the time. It's not really, there's nothing special about the letter z that says it has to point up, but it's conventional. And when describing things, when communicating to others what shape we mean, it's using conventions can be useful. They help communication. So we're doing that here. So our job is to set up a triple integral over this region. So our job is to set up the bounds of this integral over here. In the order dx, dy, dz. Okay, so we're going to draw, so before we set up this integral, so before we set these bounds, we absolutely should draw the region. So let's do that. So we know our region lives in the first octant where x, y, and z are non-negative. Okay, let me bring the integral over here anyway, so we can compute from there. So let's fill in the bounds for this integral over here. Now, we know our region, solid region E, lives in the first octant. We know it lives inside the unit sphere, so here is the unit sphere, Okay, so the unit sphere touches the first octant like this. So this is the unit sphere. And we know that the region lives below the plane where y is equal to z. So here's the line where y is equal to z. So this line, so if I look at all solutions to the equation y equals to z in three-dimensional space, I get a plane, right? I get so the y and z coordinates must, if I just forget about x, I'm just on this line in the y-z plane. But if the pair y comma z satisfies this equation, then it doesn't matter, no matter what x is, I'm going to get a solution to this equation. So we get a horizontal plane like this, a tilted plane like this. Now, if we're working with shapes that are inside the sphere and in the first octant and below this plane, so the region of integration looks like this. I'm happy about how this picture turned out. Okay, so that's the crucial thing. So once we have the picture, we can start setting these bounds. So z is so the lower bound for z in this picture is 0, right? So the minimum value of z in the whole three-dimensional shape is 0, and all points here in this bottom face they assume this minimum value of z. So let's put that in. So z starts at 0 and stops up here, right? So this point up top, the z coordinate of this point up top is the maximum value of z in the whole shape. I can tell that by looking at the picture. I could also tell that by considering various x slices and considering the 2D. You have a 2D, so each slice would pose a 2D problem, but there would be variants of the same problem. You could solve them all at the same time and find the maximum value of z in each slice, and then by comparing all different x slices, get the maximum value of z in the whole shape, and figure out it's this one. But I prefer to go by the picture in this case and recognize using the picture that this point here has the largest z coordinate of all points in this solid region. Now, what's the z coordinate? Well, we need to put some equations to work here. So what I know about this point is I know that on this point, so this point lives on this sphere. I know it lives. So this point is characterized by three things. It lives on the sphere because it's on this side. It also lives on this plane where y is equal to z. So I know this equation is true on the point because it lives on the sphere. I know this equation is true at this point because it lives on this face. And I know that x is equal to 0 at this point because it lives on the yz plane. So let's do that. So x is 0, and then we have to figure out what the relationship between y and z, what are y and z, but I can do that too using these two equations. So at this point, if I combine the two equations, I get that, so x squared, and at this point that's 0 squared, plus y squared plus z squared. Oh, I didn't put the right-hand side here. That's 1. My apologies. So plus y squared plus z squared is 1. But here y squared is equal to y is equal to z. So that's 2y squared equals 1. So y is 1 over root 2, and z. So this equation tells me y is 1 over root 2 because we're in the first octant. So we take the positive square root. And z is also equal to 1 over root 2. Okay, so the z coordinate of this point, the largest z value of any point in this solid region, is 1 over root 2. Now let's fix an intermediate value of z between 1 and 1 over root 2. So, and and then consider the z slice. So we fix z. Look at this. These things are not matching. Now they match a little bit better. Okay, so that's the z slice. So we fix an intermediate value of z, you get this blue horizontal. It's like cutting our shape with a copy of the xy plane, but lifted to height z. So we get this blue shape. Now, so the two inner integrals over here, they take place over this blue z slice. So let's do that. So the y integral, so the bounds for dy are the minimum and maximum values of y in this blue shape, in this blue slice. So the minimum value of y, so y increases to the right. The minimum value of y in this whole blue shape is here. And the maximum value of y in this whole blue shape is up top, is up here, up to the right. So what's y here? So y, so z is fixed, and so I know z. So y here, so I know that, so this line lives on the plane where y is equal to z. So y is just equal to z at the in this line segment. Okay, let me just write that down. So y starts at z, and the maximum value of y is at this point over here. So on this point, I know two things about it. I know it lives on the sphere, and I know that x is 0 there. So I know that on this point, y squared, so x squared, which is 0, plus y squared plus z squared is equal to 1. So this tells me that on this point, y is equal to root of 1 minus z squared. Okay, so that's the upper bound for y, 1 minus z squared. Right, so y starts at z being here and stops over here where it is equal to 1 over root of 1 minus z squared. That's the maximum value of y in this blue shape. Now z is fixed. I'm going to fix an intermediate value of y and increase x. So x is going to vary. And so y and z are fixed, but x will now be increasing like this. So we get these line segments, green line segments that sweep out the z slice. So x starts. So the minimum value of x in this. I'm sorry. So where does x start in this green segment? It starts back here where it is equal to 0. So this line segment, this green point, is in the y-z plane. So x starts at 0, and x stops over here. So that's in it. So I know that this point lives on the sphere. I know that y and z are fixed on this green segment, so I can express x in terms of those two. So if I just rewrite this, get that x is root of 1 minus y squared minus z squared. So that's true on this whole side over here, or the whole sphere rather, the whole upper hemisphere, rather, right hemisphere. So it's true at this point in particular, and I can just use that as my upper bound. So the rule in general, when we have iterated integrals, it's okay. So the inner bound can depend on the two outer variables. The middle bound can depend on the outermost variable, and the outer bound has to be a number. The outer bounds have to be numbers. So there you go. That's how you set this up. So the second question, so the second part of this problem, when this showed up in Professor Arm's exam a while ago, was why are these orders bad ideas? Why is the order dz, dy, dx, and dz, dx, dy, and dz, dy, dx bad ideas? right? So let me make a brief comment about this, although I don't want to take too long, spend too much longer on this problem. So why are these two orders bad ideas? I want to point out that they're both bad ideas for the same reason. So they have dz inside, the innermost variable is dz, and the other two are dx and dy. Now, when we set up a triple integral, one way to think about it is that we're working over the projection. So the two outer bounds are the two outer integrals, the middle and the outer integral, are taking place over the projection of our shape onto the corresponding plane. So here we would be working over the projection of this red solid onto the YZ plane. So that would be, so these two integrals over here are really taking place over this pizza slice. And then the innermost integral is happening, so you get one integral for each point in the projection, for each point in the pizza slice, and you go up until you go in a segment to get you get a line segment for each point in this projection, and then when you put all those line segments together, you get the whole picture. Now here, if I did it in the order dz, dy, dx, I would be working, so the two outer variables would be dx and dy in one order or another. This would mean, this could be interpreted as we're doing a double integral for each point in the projection onto the xy plane. So we would be doing a double integral over this quarter disk, which in itself is fine, but then the innermost integral, we would get a vertical, so the innermost integral would be over these vertical line segments over here. So they would stop, so for some values of x and y, they would stop on this plane, and for other values of x and y, the innermost integral would stop at the sphere. So you see that the upper bound for the innermost integral would depend on x and y, and it would depend in a funny way. So first, for points inside this, so there would be a curve. So the projection of this curve onto the xy plane would separate the two different regimens, right? So for points here, you would use the plane. For points there, you would use the sphere as the upper bound for the inner integral, and that would lead to complications. That's why these orders are bad ideas. Okay, so I would like to offer you a final example in today's lecture involving spherical coordinates. So this is not a particularly I don't want to press for time here, so I'll do a medium difficulty problem. Okay, let's do it. So example, we want to compute the volume of the following ice cream cone. So we have here are the axes and the ice cream cone. So so the shape whose volume we wish to compute is contained inside a sphere. So let me draw it like this. So we have a sphere that's not centered at the origin, and we have a cone. And our region E is above this cone and below the sphere. So let me give you an equation so you know exactly what shapes I'm talking about. So this sphere has equation x squared plus y squared plus z squared equals z. And the cone has equation z equals root of x squared plus y squared. Okay, so we need to so I think it's going to be, so to set up, so our job is to compute the volume of this region E. So E is the region inside these two. So here's E. So it's going to be useful to describe these two surfaces, the sphere and the cone, in terms of spherical coordinates. So let's do. So our problem tells you compute this volume using spherical coordinates. So let's do that. So as I was mentioning, it's going to be useful to write these to rewrite these equations in spherical coordinates. But I'm sorry, I got ahead of myself. Before we even do that, let's try to understand what sphere we're talking about here. So I'm going to do that complete the square thing. So I can rewrite this equation as x squared plus y squared, and then I want z minus something squared. So so z minus, I guess. So the cross term has to be minus z. So that's minus 2 times this guy times the other guy. That's got to be minus 2z. 2z. Sorry, it has got to be z. So this other guy has got to be a half. And then I have to add a quarter, so this equation remains true. So I can really, z squared minus z plus a quarter is this squared, and then I add a quarter to the other side, and the equation remains true. So we're talking about a circle, a sphere of radius 1. Of radius, so the radius is a half, and the center of this sphere up top is the point 0, 0, 1 half. Okay, so I know. So this already tells me something. This tells me that so the center of the sphere is at the point 0, 0 half. And the top of the sphere is the point 0, 0, 1. Because, let me just, say, this is height, the center is at height 1 half. So we now understand what sphere we're talking about. So next, before we set the bounds in triple coordinates, it's going to be useful to write write the equations describing these two shapes in spherical. So let's do that. So the first equation, so in terms of coordinates, this equation over here, in terms of spherical coordinates, this equation over here can be rewritten rho squared. So the left-hand side, sum of 3 Cartesian coordinates, that gives you the distance from the origin squared. So that's rho squared equals z squared, z. Now z is in spherical coordinates rho cosine theta, cosine phi. So let me just write that down. So this is the sphere. And I'm going to rewrite this by saying that rho is equal to cosine phi. So this is for points other than the origin. This is the equation of the sphere. That's the equation on the sphere. Now on the cone, I get z. So here, I have the equation z equals square root of x squared plus y squared. So this square root is also known as r. So in spherical coordinates, so z is rho cosine phi, and so r in spherical coordinates is rho sine phi. So that's a useful fact to know. If you had forgotten about this fact, what you could have done is take the formulas for x and y in terms of rho, phi, and theta, and then the dependency on theta for x would be cosine theta. The dependency on theta for y would be sine theta. When you add them both squared, you get cosine squared plus sine squared, which is 1. So the dependency on theta would disappear, and you just get, so the square root would turn out to be rho times sine phi. So this tells me for rho different than 0, so here assuming for points where rho is different from 0, that cosine is equal to sine. So this tells me that, so sine over cosine, that's tangent of theta, is 1. And so tangent of phi, so the tangent of phi is 1, so phi is the arctangent of 1, and your calculator or some trigonometry knowledge will tell you that's pi over 4. So the equation of the cone translated to spherical coordinates just becomes the assertion that the cone angle phi, the angle with the z-axis is pi over 4. It's really cool that you can get this angle straight from the equation by translating of the cone by translating to spherical coordinates. Right, and the equation of the sphere is, well, it's less transparent in spherical coordinates. It's this. Okay, now let's compute this volume. So the volume is the triple integral over E of 1 times dV. So let's set this in spherical coordinates. So we have so d rho, d phi, d theta is the best order. So it's usually the one you want to use. So let's do that. If necessary, you can always change course. Let's start with this order. And then we're integrating the function 1 times dv, but dv is rho squared sine phi. Okay, this is our last example. The division can go away. D rho phi d theta. All right, so let's look at our picture. So for this shape, so this region encloses the z-axis. So I need all possible theta values of theta to cover it. So theta goes from 0 to 2 pi. Now let me fix an intermediate value of theta between 0 and 2 pi, and then do this double integral with respect to phi and rho. To do that, let's look at to set these bounds. Let's look at the theta slice of the region of this ice cream cone. So here's R, here's Z, and then we have so this sphere. If I fix a theta value, and I cut this shape, I get something that looks like this. This ice cream cone just becomes like a pizza slice, another sort of pizza slice. So we're going to get this shape over here. So we're talking about, so Z so we're talking about, so we have these two equations. So this is the circle of radius a half, about the point a half, and this is the cone, Z equals R. So that over here, so up top I have R squared plus Z minus a half squared equals a quarter. And down here you have the cone. So our shape, the theta slice, for every value of theta get the same slice because the shape is symmetric around the z-axis. This is our region. Now let's use this picture to get the bounds for rho and phi. So phi goes from okay. So we know this angle. So we know this angle here is pi over 4, right? That came straight from the equation of the cone in spherical coordinates. So this is pi over 4. So phi goes from 0 up here to pi over 4 up there. So these are the two bounds, 0 and pi over 4. All right. Now let's fix an intermediate value of phi and shoot out a ray. So we fix an angle theta, which is like a longitude we fix an angle phi, which is akin to a latitude. So we pick a direction in the sky and shoot out a ray in that direction. And the bounds for rho will be the moment you enter the region and the moment you leave the region. So in this case, the bounds for rho are 0 because we enter the region immediately, and you will stop when you hit the sphere. The equation of the sphere in Cartesian in spherical coordinates is rho equals cosine phi. So because it's not around the origin, it's a little bit more complicated. So that's the equation you get. So rho up on the sphere is equal to cosine phi. Okay, so this is number of, so this triple integral can be evaluated in a straightforward fashion. I will skip this calculation in the interest of time. Let me just mention that we're really integrating. So first of all, theta doesn't appear in the two inner integrals, so that just contributes a factor of 2 pi. In the two inner integrals, we're really integrating a product of a function of rho and a function of phi. So when we do it, actually I should be careful because the upper bound depends on phi. So let me interrupt this comment right here and just tell you the answer for this integral, which you can verify for yourself later. And just say that after some work, this turns out to be pi over 8. So, so that's it. Thank you for staying tuned until the first midterm, which is next Monday. And I hope this lecture, this review, will be useful to you practicing training for that exam. So if you have any questions, do let me know by email. So thanks for listening, and I'll see you guys next time.